calculate the B field from a line of current at some distance r away from the wire. On the diagram to our right, we can see a current wire, a wire carrying a current, which we would say as infinitely long, and some point P, which has a perpendicular distance r away. In this question, we will try and solve this by using the Biot-Savert law. This is defined to be the following. Delta B is equal to mu naught over 4 pi I delta L cross product with r hat over r squared. We will see what these variables mean as we go through the question. Firstly, we see this cross product thing here, and that's quite annoying, especially if we're using little elements, which suggests that we will do some sort of summation, aka an integral. So we want to get rid of this. That's a good idea. And also, this diagram is still quite empty. I feel like we're lacking some of the aspects we want to write down. The first suitable thing, perhaps, would be to draw a small element, delta L. And then draw some lines, perhaps. So a line from here to P, that would be the distance R from the element of the length element to the point we're interested in. And then we can define this length here as perhaps the length of the wire. And then we can integrate for this side of the wire and then also this side of the wire. Because of how trigonometry works, considering it as this and this separately may be more useful, although it doesn't make much of a difference in the end. Let's call this angle here theta. So what do we do now? Well, firstly, we want to get rid of this cross product thing. We know that if there's some vector A cross with some vector B, that is equal to the magnitude of A, magnitude of B times sine theta multiplied by the unit normal vector. Because a cross product gives a vector, we need this vector to make the result a vector. Without this is only a magnitude. However, if we want to find the magnitude of this, then we can just get rid of the vector. And then if we have just some number, then that would be much easier to integrate. That's nice. But we still need to know the direction of the magnetic field. We can work this out by using the right-hand screw rule. Using this rule, we can work out that the current is coming out at the left side from the left-hand side of the wire, and it's going back in on this side. So we know at point P, the magnetic field is going inwards to the page. That's nice. So we can simplify this equation and get rid of this cross product. In order to get rid of this cross product, we see that we have a delta L and an R here. And where are the directions going? Delta L is going this way and R is going this way. So the angle we're concerned about is this angle here. Let's call it phi. And that phi is equal to pi over 2 minus theta. So we can rewrite the Biot-Savert law in the following way in this question. Mu naught over 4 pi I. And then since we're doing a cross product and only taking the magnitude, this would only be the size of the magnetic field. I times delta L, and then the magnitude of r hat by definition is 1, so we'll ignore that. And then sine of pi over 2 minus theta over the r squared. So here we realize that this can be written as cos of theta. That's nice. And it turns out in this question, it's much nicer to change all the variables with respect to theta, just because of how hard the integral is. And the integral becomes quite simple with this when we change the variables to theta. So let's look at this. Let's do some trigonometry. Tan theta would be equal to L over R. So then that implies that L equals R tan theta. And if we take the derivative with respect to theta, we result in R, which is a constant, sec squared of theta. That takes care of delta L. So we can just say that implies that delta L is equal to R sec squared theta d theta. Now we have written delta L in terms of theta, which is nice. Now we have this R squared. This R squared also changes with theta, because say we're adding all these little elements up. So that would mean that say for this element, the angle will be different and the distance r would be different too. So that's also a variable that changes. So we need to write that in terms of theta too. How can we do that? Let's consider the cos of the triangle, cos theta. Cos theta will be equal to big R over R. And that implies that little r equals R over cos theta. And therefore R squared equals R over cos squared theta. And that can be written R squared, over cos squared theta. And that can be written as R squared sec squared theta. So we have converted delta L and R. These are in terms of theta. These are constants. This is also a constant. So nice. Now we can perform the integration. As these elements of length delta L become smaller and smaller and tends towards 0, it is denoted as dl. This is just because as we decrease the length, dl, the summation becomes a better and better approximation of the real value. And so delta L becomes infinitesimally small, and that's so we can use the following notation. dB equals mu naught over 4 pi under I2, that's the constant. dl can be written as this, r sec squared theta d theta, and then we have a cos theta, and then divided by r squared, which is written as this, r squared sec squared theta. What's really nice about this is the sec squared thetas cancel out, and then the big R can have some cancellations too, and then we result in some integration. So let's integrate both sides. Integrate of dB between integral of all the magnetic field elements from each of the little dl elements which has current flowing through will just be the total magnetic field, and we'll denote that as B. And that is equal to, let's put the constants on the outside, 4 pi mu naught I over 4 pi integral of cos theta d theta. And the limits, what would the limits be? Well, theta, if this is an infinite wire, theta will tend to 90 degrees, and that will be the maximum value, and also 90 degrees on the other side. So if we want to perform this integral, we can simply use limits of pi over 2, which is infinite wire to this side, and then minus pi over 2 for the infinite wire going upwards. And just for a note, this is the same as doing an integral of pi over 2 to 0 cos theta d theta added with the integral of minus pi over 2 0 cos theta d theta. If this is basically what we're doing, because we're considering this infinite wire and the magnetic field produced on this point, and then this wire, infinite wire, and its magnetic field, and the relevant angles are these, considering this side to be positive angle. But we can write this as this because of the function of cos, where the area from 0 to minus pi over 2 is the same as the area from to pi over 2. And this is known as an even function. So let's perform this integral. This is equal to mu naught, oh, I forgot an r from here, mu naught I over 4 pi r, and then integral cos theta is just sine theta with respect to theta, from pi over 2 to minus pi over 2, and that is equal to mu naught I over 4 pi r sine pi over 2 is 1 minus sine minus pi over 2 is minus 1, and that just gives mu naught I over 2 pi r. And that is the magnetic field at some point P away. And we have determined that the magnetic field will be into the page. And that's how to do the question.